Here we've got a part of our foundation Fieldbus system in the instrumentation lab with our Turk multi-point junction brick or connector right here, the coupling device. Into this we happen to have one transmitter plugged in. This one transmitter comes over here. This is a Rosemount 3095 multivariable transmitter. It is also a foundation Fieldbus. You can see that right here on the tag. It says foundation Fieldbus. You also see the flying F, the stylized letter F, which is the foundation Fieldbus logo for all foundation Fieldbus devices. That's really the main indications that this is not a 4 to 20 milliamp transmitter. It's foundation Fieldbus because it says so directly. The other hint, the other indication, is what we see right here. Where it wires up, we see it says Fieldbus wiring. I see 3 terminals. The middle one says NC. It does not mean normally closed. It means no connection. The other two say Fieldbus wiring. One important note here is that you don't see any polarity marks on that. There's no plus and minus. That's common of a lot of Fieldbus devices. Not necessarily all of them, but a lot are polarity insensitive. You can hook them up any way you want. It's pretty nice. But Fieldbus does have a definite polarity in the wiring, and some devices need to be respectful of that polarity. So let's go ahead and get your meter. I'm going to hold this fluke meter here. We're going to take some measurements. I'll hold this cable out of the way. Let's first measure DC volts. Let's set up for DC volts. And we're going to hold the meter in such a way. Here we go. I'll just put the cable here. I'll hold the meter. I'll just hold it like this. There we go. So now we're looking at DC volts. Go ahead and measure across those 2 leads of the transmitter and see what we read. 25.4 volts. Okay, it's nominally 24 volts on our system we have right here. Typically you go anywhere between 9 volts and 32 volts or so on a Fieldbus system, but we're running somewhere around 24. That's what we expect. Now I want to show you how you can actually see data going back and forth on the Fieldbus line. Let's switch this to AC. Now a fluke meter like this is very good at discriminating AC signals from DC. So when we set it to AC, it's going to ignore the DC and only show us the voltage that varies back and forth. And that of course is going to be our data, our digital data. Go ahead and measure that. So we're reading about 320 millivolts RMS. It's going to be a Manchester encoded square wave signal, and it's dancing around here because it doesn't really have a steady RMS value. Now the foundation Fieldbus specifications for a good healthy signal typically range between 350 and 750 millivolts, but that's peak to peak. But what we're showing here is RMS, which is a little bit different. So we'd have to do our peak to peak measurements using an oscilloscope instead of a voltmeter. However, this is a simple gross test. And if you took enough of these readings, you got used to what the signals look like in an RMS fashion, you could use this as a guide too. You could see what a poor system looks like and what a good healthy system looks like. This I happen to know is a good healthy system. So we're looking at about 320 millivolts, and that's again RMS voltage. An oscilloscope would show the actual square waves, and we'd be able to make a better determination of peak to peak. So that's a very simple qualitative test of a Fieldbus system. We are communicating. If the communications were to stop for any reason, we wouldn't see this AC voltage. We would just see the DC voltage, the DC power. And of course, if a cable breaks, we wouldn't even see that. So very simple tests we can do on a Fieldbus system with a multimeter.